Hi, welcome back. My name is Charlie Solis. I'm here today with my Tesla turbine and my vacuum chamber condenser for the cold steam, vacuum steam cryophorus generator turbine system that we're working on right now. I'm going to go through the shell and tube heat exchanger that I've assembled with a keg and some brewery fittings and a custom copper pipe heat exchanger I put on the inside of it. But before I get into that, I'm going to give an update and a shout out to all my Patreon donors. Thank you guys so much for all the help you guys give me. Can't do what I do without what you guys do. And if you guys have been at least 3 months in now, if you're in tier 2, you should have access to a free t-shirt. That's a Tesla Turbine Energy t-shirt. Or if you're in tier 3, you have access to a hoodie. Just gotta update your shipping address if you haven't received it already. It's waiting for you guys right there. So check that out and follow me while I'll go through this shell and tube heat exchanger. Here we go. So I want to start out with saying I've got technically a half barrel, full keg, stainless steel vacuum chamber. I do a video showing it capable of holding the vacuum. I explain about how the electropolishing on the inside of not just the stainless keg, but the other stuff helps make it easier to pull a really, really deep vacuum without a lot of off-gassing from the crevices and cracks that are inside the surfaces of all the fittings and everything in the whole system. There's going to be a vacuum chamber that's going to go with the turbine over here that I will go through in a future video. We're still working on the build on that. What we've got here is a shell and tube copper heat exchanger that I custom made to go inside these 4-inch tri-clamp T's that go to 2-inch tri-clamps. These 2-inch fittings will go to the vacuum chamber that the turbine is in and is exhausting out to. So from the turbine, it will go into the vacuum chamber and then through 4 pipes. From those pipes, it'll go through 4 intercoolers, and then from those intercoolers, it'll go into this shell and tube heat exchanger. So the intercoolers are an air to steam heat exchanger condenser. This is an steam to water shell and tube heat exchanger. And then inside the keg, I'm going to be putting about 100 feet of PEX pipe just circling in there. Now I know PEX pipe isn't the best, but the 4-inch tri-clamp hole here isn't the easiest to get things in and out of. I should have gone with the 6-inch one. I know for the future builds that's something I'm gonna do, but the PEX pipe will be really easy to feed in. I don't really need the full vacuum area inside this to be available. I'd rather have a large volume of cooling water in the system inside, able to continuously extract heat. For the turbine, I'd rather be able to extract as much heat as possible so that I can maintain the vacuum as deep as possible. And the lower the vacuum, the more the pressure gradient is across the turbine for more power out and higher efficiency as well. Okay, so I've kind of already removed some of these to begin with so that this will be a little easier. I don't know if you can see it from there. I've got another tri-clamp piece on here that goes in from a 1/2 inch in, and it will go into these back and forth, and then it'll come back up and come out this side for another one. So the water will come in, go back and forth, back and forth, back and forth, back and forth, then go all the way to the bottom, circulate around a large coil of PEX pipe, and then come back up and go out this side. I will more than likely probably send the water the coldest at the bottom so that I can circulate the water and it leaves out the top here the warmest. The warmer you can get the water, the warmer it is going into your boiler or heating into your room or however you plan on using this heat. Now, a little FYI, normally these quick release systems you cannot use for vacuum chambers because they work on a positive pressure seal. However, this positively pressured cooling water pipe will be inside a a lower pressure vacuum chamber so that the water inside here will always have a positive pressure, and I won't need to worry about any sort of leaks because it's inside the vacuum chamber. If I tried to pull a vacuum inside this heat exchanger, these would not hold the vacuum. Just a note for the future. These then go down to the bottom. I'm not going to take this full thing off. You can see these still slide a little bit in here. One of these pipes goes down and and I'm going to have it come back out. Go back out to the fitting on right here. So this will have a water pipe that comes to any sort of heat exchanger. if you're looking to do a system like this yourself, when you use cooling water in the turbine, you're then going to have to take that cooling water as it's warm and then make it exchange the heat with the air. I highly suggest checking out the Tesla fountain steam condenser heat exchanger video that I have. It's an idea that I have come up with for using the Tesla fountain to work as an air to water heat exchanger for cooling water. In the fountain patent, Tesla talks about it working to help cool down an area that it's in, that it's able to exchange heat really well. He doesn't talk about using it as an actual heat exchanger for the steam turbine system, but it's my hunch that that was absolutely his intention for it, because it was the very next thing that he patented after the Tesla turbine. And I have to believe that after working with the Tesla turbine and the steam systems, that he was thinking in terms of condensers and boilers and cooling water, and he then comes up with a fountain that could possibly be the most efficient way to circulate water to then exchange heat with the air, because it reutilizes the falling energy that was used to lift up the water to reduce the amount of energy that the pump has to use to lift. Now, it's not not an infinite loop, but all you have to do is make up for the friction losses as it flows. He says that for an 18-inch lift, which is a pretty decent sized fountain, it's an 18-inch fountain, about a 3-foot diameter base, can move about 100 gallons per minute with 30 watts. That's pretty impressive. Check out my other video where I built a radiant water heating system for the workshop here. We're going to be circulating the water from the cooling water, which will leave warm, through the radiant heating system for the workshop here, so that all of the loss heat that doesn't get used in the turbine will end up being used for heating into the garage. What that means is irrelevant to how efficient the turbine is actually turning the heat energy into electrical energy. Any of the energy that doesn't get used has to be evacuated by the condenser to maintain the vacuum. By doing that and using all of that heat energy to heat up my workspace and eventually soon my house, we'll be able to bring up the whole total system efficiency up into the 75 to 90% efficient, because any loss in the turbine goes to heating. And while it may not be able to provide us all of the electrical energy we need for an entire day or the peak demands, it can reduce most of our electrical needs, and all the loss eliminates all of our heating needs. Bear in mind that when we do this system, irrelevant to how good or how efficient that turbine is to making electricity, the fact of the matter is that this heat that's not used is always still available for heating. And now I know not all of you guys live in cold areas, but I'm in Detroit right now. It's like anywhere from 3 to 15 degrees Fahrenheit, pretty cold. And even with this radiant heating system I've got, we can keep the garage up to at least 55 to 65 degrees on a good day with just some propane and a hot water heater. It makes it so I can do a propane heater in this garage without having a big torpedo flame that the heat that comes right off of it just goes right up to the ceiling and then out of the room. By doing it this way, I can dump all of the heat into water, store it in a water tank, and then slowly release or circulate that water through radiators that are in my workspace here that'll help heat it. Eventually I'll be able to make another one in my house and do the radiant heating down and back and forth between the floor joists in my first floor. All right, thank you for being here for me to do this walkthrough for you. I'll have a lot more updates soon for the Tesla turbine that we're doing. Every bit on this is now either aluminum or stainless steel, except for the end plates on here that are still polycarbonate, because I would like them to be a sacrificial end plate in case something goes wrong. It might melt the plastic, but I can take my heat gun to it and scrape the plastic off, cut new polycarbonate casing pieces and move on. If the casing was all aluminum, there's a very likely chance that the aluminum turbine could literally fuse to the aluminum case because of how fast it's going and how much heat will be generated if they start to touch off. But yeah, stay tuned for more videos on that. If you haven't seen any of my Tesla turbine stuff, I have multiple videos. One where the best dyno test we've done right now is 2.75 kilowatts and 6.22 foot-pounds of torque at 4150 RPM, which they tell you Tesla turbines don't have torque and they have to go fast. We're proving it wrong. I also have another video that shows the turbine being used with compressed air energy storage systems, essentially 150 psi air that I use to power a 1200 watt light load, like a light bulb load, not like it's a light, like not heavy, that I use to power a 1200 watt light, and then test the difference between room temperature compressed air and then 75 degrees Celsius heated compressed air. to show the difference in energy outputs for the room temperature compressed air and then the heated compressed air, as well to use that as a kind of an early benchmark to give a graph or a trend line to see what will happen as we increase the temperatures higher and higher and get into combustion temperature ranges with the turbine. So fingers crossed, we'll soon have more updates on that. We just got the new CNC machine set up. This guy can do stainless steel and all the other harder metals. So we've got all the stainless steel here to make a full version of this out of all stainless steel for full high temperature combustion. That'll be coming up soon. Just got to finish working on this. Still have some minor things for the system to work on. I'll have more updates for you coming soon. Take care, guys.